to respectfully acknowledge and recognize our responsibility to the original and current caretakers of this land, water, and air, the Cahuilla, Tongva, Luiseño, and Serrano peoples, and all of their ancestors and descendants, past, present, and future. Today, the UCR campus is home to many indigenous peoples from all over the world, including UCR faculty, students, and staff, and we are grateful to have the opportunity to live and work on these homelands.
Good afternoon, everyone. My name is Xiaowen Cai. I'm the chair of the Department of Physics and Astronomy. I'd like to welcome you to the Frontiers of Physics, a celebration honoring our very own Nobel Laureate, a distinguished professor, and endowed chair for teaching, research, and service, Professor Barish. For being awarded the 2023 National Medal of Science by President Biden. We have an amazing lineup of speakers, but before we start, I would like to welcome and acknowledge the presence of representatives of a few elected officials present here today. First, Rachel Moore, Constituent Services Representative from the Office of the Honorable Mark Takano, who represents the 39th Congressional District. Shaira Hernandez, Director of Stakeholder Engagement from the Office of the Honorable Raul Ruiz, who represents the 25th Congressional District. Jet Benavides, Staff Assistant Field Representative from the Office of the Honorable Ken Calvert, who represents the 41st Congressional District. Viridiana Aguilar, Senior Constituent Services Representative from the Office of the Honorable Pete Aguilar, who represents the 33rd Congressional District. Stephanie Camarillo, District Representative from the Office of the State Senator Richard Roth, serving Senate District 31. Daisy Arteaga, Senior Field Representative from the Office of the Assembly Member Corey Jackson, serving Assembly District number 60. Thank you very much for your presence. And now, to get us started, it's my pleasure to introduce to you the UC Riverside Provost and Executive Vice Chancellor, Liz Watkins.
Thank you, Shen-Wen, and welcome everyone to our talks this afternoon on the frontiers of physics. We are very fortunate today to have two world-renowned physicists as our guests and speakers today, Dr. Art McDonald and Dr. Jang-Ki Jung. Speaking first is Dr. Art McDonald. Dr. McDonald is Professor Emeritus at Queen's University in Kingston, Ontario, where he served as the first director of the Sudbury Neutrino Observatory. He continues to be active in basic research in neutrinos and dark matter. Among his many honors, he was named an Officer of the Order of Canada in 2006. In 2015, he was awarded the Nobel Prize in Physics for his contribution in discovering the oscillations of neutrinos, which prove that neutrinos have mass. Dr. McDonald is here today not only because he is a renowned physicist, indeed a Nobel Prize-winning physicist, but also because he is good friends with Dr. Barish. And we are so pleased he could join us today. Please give a warm welcome to Dr. Art McDonald.
So it's a real honor for me to be here today to speak at an event celebrating a very good friend of mine, Barry Barish, the recipient of the National Medal of Science. Is a fantastic accomplishment, representative of his service to the nation, as well as his service to science, which is represented by the Nobel Prize. And I've known Barry since we were both at Caltech together back in the 1960s. That's 1960s. But it was quite a while ago. And he's been a fantastic mentor to me, as well as all the wonderful things he's done in science. So we're here today to celebrate the establishment of a center in experimental cosmology. And so let's see. Well, these buttons don't, oh, I've got to turn it on. That's a good idea. There we go. Let's try that. There we go. So experimental experimental, what is that word anyway? You need to be a little bit careful, because so when you name your center something like that, you can get yourself in a little bit of trouble, even with spell check. It'll you know, you have to be really careful as you write the title each time, because it'll try to switch it over to something that's a little more understandable. I can just show you another example that makes me very conscious of the fact that this sort of thing can happen. Not everybody will understand those unusual words that the general public doesn't use. So here's an example of a letter I got a couple of years ago from the Human Resources Department in our university. And so just to show you that those things can happen. But why did I try to make light of this at the very beginning? Because you know, what we do is fun. Science is fun. And that's something that Barry has really, you know, it exemplifies the sort of things that he's done over the years. He's very interested in teaching and inspiring the next generation to get into this fun game, which is trying to understand how the universe is made up and how it evolves. Actually, Sean Westerdale is in the spirit of this. I was talking to him earlier today. He's one of the new junior faculty here at Riverside, and he said, well, you know, that's not such a bad term. We're studying the makeup of the universe after all. So I think that's the sort of spirit that we try to have as we do these things. And, but it's also a very serious topic in terms of trying to understand how science works. And Barry has been really a wonderful example of someone who always does things that have fundamental and significant importance at the time that he's doing them. I mean, back in the 1960s, going into the 1970s, at Fermilab, he was inspired to help develop a beam of neutrinos that can be used to scatter off of nuclei, and in the process then established a new element of what has now come to be called the standard model for elementary particle physics. But at the time, that was something new, and this was one of the first things establishing that. And then at the SLAC, Stanford Linear Accelerator in Palo Alto, he did further experiments which detailed that weak neutral current in even greater detail and testing of the standard model. Also, he was really one of the first people in the game of doing experiments in an underground environment, where what you use is the rock above you to try to get rid of the cosmic rays. In Canada, we're very familiar with the fact that cosmic rays exist because they're another component of them, similar to the ones that could penetrate through into our underground laboratories if the rock were not getting rid of them, are the ones that cause the northern lights. And so you can imagine that if you have these rays from outer space that are, in some cases particles from outer space that are making the atmosphere glow like that, what would happen to your detector if you didn't get rid of more than 1 million of them, or 1 million times lower flux by the time it gets to your detector because you're underground? And so Barry was a pioneer in studying a search for what are called magnetic monopoles. You know, magnets always have a north and a south pole, but these are unusual objects that were proposed to exist in certain grand unified theories that go even beyond the Standard Model back in the early 70s and set limits that are, you know, some of the most substantial ones in the world still at this time, that showed that they were not observable, and therefore having an impact on those theories, and also use the same detector to confirm the oscillation of atmospheric neutrinos, which is something that the Nobel Prize was awarded for, along with our experiments, which I'll talk about a little later. Now, Barry went on to be a co-leader of one of the two massive detectors that were proposed for something called the Superconducting Super Collider, SSC, which unfortunately did not make it eventually for funding. But again, an example of the fact that when you're looking for leadership in a project, particularly some of these massive national projects, Barry is the person you look to. And in fact, that's what happened in 1993 when people from Caltech and people from the funding agencies themselves came to him and asked if he would take over the leadership of the LIGO experiment, which is searching for gravitational waves. And that experiment, in terms of what Barry did to set it up in the first place, and then what was done later to make it even more sensitive, which he had a significant part in as well. Advanced LIGO actually observed the first signals where basically what you're looking at is space being distorted by, in the case of the things they observed, by the collision or merging of black holes. Very tiny signals, but really it opened a whole new area of observation in astronomy. Now, from 2004 to 2012, again, the international community came to him to lead what's called the International Linear Collider, definition of an accelerator which would be the next generation experiment past the current highest energy accelerator at CERN, the Large Hadron Collider. It's just a measure of the respect that he has for, or the people have for him, which from my experience is also a measure of the fact that he has respect for the people he works with, and therefore is a natural born leader. I experienced that personally when we were starting the Sudbury Neutrino Observatory, which is the measurement of neutrinos from the sun, for which I was eventually awarded the Nobel Prize on behalf of the team that did this work. Barry was chosen by a committee formed by the funding agencies of Canada, US, and the UK to be an external technical expert. There were only two of those, and he was very, very steady in coming to every one of those meetings for a number of years through until the commissioning of the experiment. And for me, his experience in leading large international collaborations and his experience in underground laboratory work through the macro experiment was tremendously valuable. And so I learned a tremendous amount from him and regard him as my mentor in this area. So let's talk about this area. What I want to talk to you about today is experimental cosmology. I'm being very careful to use the right word. Really, it means trying to understand how the universe has evolved, but also understand what the composition of it is. And the experiments that are used are extremely large. You can see the LIGO experiment where these are kilometer-long arms on an experiment that's comparing whether the Earth has contracted more in this direction than in a perpendicular direction due to the passage of a gravitational wave. Very sensitive. 1 kilometer cubed of ice under Antarctica has been instrumented with light sensors that look for the highest energy events from neutrinos. And in the lab I work in Canada, Snow Lab, we have an original experiment, the Sudbury Neutrino Observatory, and also a number of other areas that are looking for dark matter particles. And this is really spanning the whole gamut of size in the universe. We start with the tiniest particles we know in terms of what's the distance over which they influence other things, neutrinos. We span through quarks, which are the components inside protons and neutrons, which are in the nucleus of an atom, electrons going around that atom. But we also study the sun, and that's what the Sudbury Neutrino Observatory did. We study now in an incarnation of it called SNO+, neutrinos from the Earth, which is a measure of uranium and thorium content, which it turns out that 40% of the heat coming out of the Earth comes from radioactive decay from those particular elements. And you can see they're actually antineutrinos, antiparticles, but you can detect them and essentially do geology on a very large scale, down hundreds of kilometers into the Earth. Our Milky Way galaxy is a prime example of something that's held in place in its current shape by the existence of dark matter, which is the objective of a number of different experiments in this area of our laboratory and in others around the world. That dark matter is distorting these images because light that travels near a very massive object follows the distortion of space that occurs near that object. The solar eclipse we had a few weeks ago, which happened to pass directly over Kingston, where Queen's University is situated in Canada, was first used to prove that Einstein's theory for the fact that space is distorted in the vicinity of the sun results in light from stars being deflected as it comes past the sun. Having the eclipse meant you could now observe these stars and see, in fact, that their position had moved. And so that gravitational lensing, it's called when you use it large scale, tells us that dark matter particles exist that are 5 times in the total mass compared to all the ordinary matter that we know about, that we're made of, the stars are made of, and so on. And finally, the overall structure of the universe on the largest scales is influenced by this dark matter. And so by studying the sort of things I'll mention, which will be the components of the Experimental Cosmology program here at UC Riverside, you really are studying the entire universe, everything from the smallest scales to the largest. And so, what are the questions you're trying to answer? Well, what makes up our universe? What are the different components? What are the laws of physics for those things? How do the stars like our sun burn? And it turns out they produce a large fraction of the elements from which we are composed through the nuclear reactions in the sun, which is another thing we can study. Of course, the gravitational waves for which Barry received the Nobel Prize are from colliding black holes, and black holes have become a big part of cosmology these days. And these cosmic rays that we're going underground to avoid, other experiments try to measure. And what is the origin of them? They're very energetic compared to even the highest energy accelerators on Earth, and how is that produced? So just a quick review, because I was told to give this talk to people who may not be particle physicists themselves. As I said, quarks, and here you see the components that we think make up the so-called standard model, 3 different generations, as we call them, of quarks, and 2 different types as well. And then neutrinos, 3 different types of them. The electron you're very familiar with, that's what flows in our wires, and heavier versions of them. But really it's this first column here that makes up our world that we're familiar with. 3 quarks come together to make up a neutron or a proton. They have 1/3 charge, and they can be combined to produce either a 1+ electrical charge proton or a neutral neutron. Those protons and neutrons are in the nucleus of an atom. The electrons go around the outside, and it really is the effects of different electron configurations that gives you chemistry and basically everything else you experience in the world. There's a limited set of force carriers. The one you're probably most familiar with is the photon, and the theory is such that the photon goes from that light that's blinding me to my eye, and that's the way the force is exerted on my eye by those electrons that are jiggling up in that light bulb. We do not have a way of getting gravity into this formula, into this model yet. We do have the Higgs boson, which is a central element of the model, giving mass to all of these particles. Now, neutrinos are unusual particles that you'll hear more about from me and from Professor Jung later on. They only feel the weak force, and of course gravity, if they have a finite mass, which we now know they do. They're produced in radioactive decay. The decay that's happening in a banana actually produces neutrinos, but they are so lightly interacting with anything that they can pass through the distance that light travels in a year of lead and only have a 50% chance of hitting anything. So don't worry about eating a banana. You're not going to end up with problems from neutrinos. They're also produced in the nuclear reactions that power the sun, and because they penetrate through anything, we can observe them coming from the core of the sun and see what it is that powers the sun. What are the nuclear reactions that are doing that? Each of these particles has an antiparticle. You're probably familiar with that from positron emission tomography, which is a medical procedure that's been worked out where they inject a radioactive source that's going to emit these antiparticles to the electron called positrons. When they find an electron, as they may, for example, in your head, if that's where the blood carries the radioactive material, they produce two gamma rays that are absolutely back-to-back because you have to conserve momentum, and you started with positron and electron essentially at rest. So positron emission tomography basically is putting a series of detectors around your head and connecting the dots between the two detectors that detect the gamma rays produced by the conversion of matter into energy. And you get enough of these, you connect the dots, you see where the blood is flowing and where the blood is not. And it can even be used for things like seeing what part of the brain lights up when you're listening to music. It's a fascinating technology. My master's thesis was studying the properties of positrons in materials. 10 years later, we had positron emission tomography because the engineers picked up the basic properties we had determined. So it's an example of what happens when you do basic science is you eventually can help humanity by the application of this knowledge that you obtain. So because they come from the sun, then we can observe the sun, and there is the possibility that we might observe them from the Big Bang, but that's a very difficult thing to do that people are still working on. Dark matter particles, the things I mentioned that are 5 times as much mass as the things that I just described, we don't know what it is. It doesn't fit anywhere in what I just showed you. And so it's a fantastic scientific endeavor to try to observe it. Neutrinos, let's talk about them for a moment. Most of what I say here is in what I just said a moment ago. 3 types. They only feel the weak force. The type that's produced in the sun, which is the electron neutrinos, are not supposed to change their costume to be a mu or a tau neutrino, but in fact that's just what we observed coming from the sun, and the Super Kamiokande experiment observed that for atmospheric neutrinos, and that's what the Nobel Prize was awarded for. There are a lot of neutrinos coming through you right now. These ones are very low energy. They're left over from the Big Bang, so they barely do anything. The solar neutrinos are the most abundant of the rest, and there's something like, well, more than 1 billion per second going through a space on your, an area on your body equivalent to your thumbnail per second. But only maybe once in your lifetime will one of those neutrinos stop in your body, and probably only if it happens to hit you in your eye, and that eye happens to be closed, as many eyes are by the time I get to this point in my lectures usually. But were that to happen, then you might see a little burst of light like we do in our detectors, and that's the way we detect them. But they're very, very hard to detect, and so solar neutrinos is what we observed. Atmospheric neutrinos is what the Super Kamiokande experiment observed. The ice cube experiment under the ice in Antarctica is looking for these. There are a number of experiments looking at them from reactors. They're actually antineutrinos produced in nuclear reactions in the reactors. And Kushiba, using the predecessor to the Super Kamiokande experiment, an experiment called Kamiokande in Japan, got a Nobel Prize for the observation of neutrinos from a supernova, because there's a tremendous number that are produced in a very short period of time from a supernova. They shared it with Ray Davis, who also was the first one to show that there are too few solar neutrinos. And the fact that Davis had found in a previous experiment that there were too few of those solar neutrinos, and yet we didn't know whether it was because the calculations of how many were being produced in the sun were incorrect, or whether there was something else happening with the neutrinos, is what inspired us in the first place to do the Sudbury Neutrino Observatory using a material called heavy water. 1 in 6,000 of the water molecules you drink has an extra neutron. We borrowed $300 million worth of it and put it in a transparent vessel looked at by 10,000 light sensors 2 kilometers down in the Creighton mine near Sudbury. And we were able to observe the difference between the number of neutrinos that were still electron-type neutrinos and the total number of all neutrino types. And that observation was enough to show that neutrinos were definitely changing their type, because only 1/3 of them were still electron neutrinos. And we had a clear measure by measuring 2 things and didn't have to rely on any calculations of how many are being produced in the first place. And that is, in fact, what led to the Nobel Prize, or at least our contribution to it. The Super Kamiokande experiment did similar things, observing neutrinos coming from the atmosphere and oscillating or changing type as they came across the Earth. And you can see how big this is. It's about 50,000. We were about 1,000 tons. They're about 50 times that big. And you can see people in a little boat here in this experiment, which is still being used for many experiments in Japan. So the standard model for elementary particles has to be changed as a result of this. These neutrinos apparently don't get their mass in the same way as others do through the Higgs boson mechanism. We also were able to measure the number of neutrinos produced by the fusion reactions in the sun, and we did that quite accurately, to 10% or so. And of course, it's the same or similar reactions to what's being done for fusion power reactors here on Earth, and therefore we've contributed to the knowledge of that. But of course, in terms of where we come from, which is in part a substantial objective of experimental cosmology, trying to understand our origins. In terms of carbon, nitrogen, and oxygen, it looks as though our origins of those materials are in fact the sun itself, or stars like it. And so it's fundamental from that point of view as well. So this is the Big Bang Theory, not the TV show, but fairly well, they did a pretty good job actually of representing things well on that TV show. In fact, The technical advisor for the show was a student of ours when I was a professor at Princeton in the 1980s. He's a professor at UCLA now, and was also the technical advisor on Interstellar. And he did a pretty good job of making sure that all the formulas on the blackboards were correct, and also that the experiments they were doing were not too crazy. I actually got invited to be Geek of the Week at one point and go and sit in on the filming of a program. However, let's get serious. We now think that this is what has happened in terms of how the universe has evolved. About 13.5 billion years ago, there was a major expansion of the universe. A tremendous amount of energy went into producing those fundamental particles I mentioned. By the inverse of this positron annihilation, this is a case where energy becomes mass rather than mass turning into energy. E equals mc squared, in this case, is energy converted to mass. Particles and antiparticles produced, we think, in equal numbers in the original process. And so all of the ones I mentioned, quarks, electrons, neutrinos, were produced back then. You see the numbers here of the time and also the temperatures, enormous temperatures back in those days. After about a microsecond or so, you come to the point where the quarks can form protons and neutrons. After about 3 minutes, they can start forming into nuclei. After about 300,000 years, those nuclei are cool enough from this expansion that you can actually form atoms, neutral atoms, and it's at that point that light begins to shine through. And that light is detected these days, cosmic microwave background it's referred to, and one part of the program in experimental cosmology here at Riverside will be understanding that cosmic microwave background in more detail. After about 1 billion years, then you start to form galaxies and stars, and after about, it says 15 here, we now think it's about 13.6 billion years, we have what we have today. So you've been hearing a lot about the James Webb Space Telescope and why it is particularly interesting. One aspect of that is that it now has the sensitivity to go back about 12 billion years, back to basically this point here, where the first stars are being created. Later stars are often created because there's a collapse called a supernova that distributes the matter and then forms another star, but it's looking now at the very first formation of stars in the universe, and that's why it's particularly interesting to astronomers. Now, here at UC Riverside, cosmology theory is being done by the individuals that you see here, and I'll pop up these little white blocks from time to time as we go forward so you can see the way in which experimental cosmology, and theoretical in this case, happens here at UC Riverside. But there's a big mystery in the sense that we think that there were equal amounts of matter and antimatter produced back in the early universe. Where's all the antimatter? You don't see positrons popping up and annihilating with electrons, so you get gamma rays coming out of your breakfast cereal. You really have very little antimatter compared to matter, except when it's emitted from things like radioactive sources. So what happened? Where did all the antimatter go? A very substantial theory that people think is quite credible and could be the explanation for that involves the properties of neutrinos, which can be studied in a certain type of radioactive decay in which 2 electrons are emitted in a certain decay and no neutrinos, because the neutrinos can have a symmetry such that no neutrinos are emitted. This is something that's being sought in what are called double beta decay experiments, but also there are experiments being done to look for the differences between for example, muon neutrinos and muon antineutrinos in terms of whether they behave different, whether they're matter or whether they're antimatter, and Professor Jung will talk a bit about that as we go forward. Okay, we did move. And this is, in fact, the experiments that he will talk about, and I'll just give you an overview. The idea is to shoot a beam of neutrinos produced here in the United States, produced at the Fermilab accelerator, through the ground to a underground laboratory 1,300 kilometers away in North Dakota, and to look for a difference in the number of neutrinos that are observed, whether you use neutrinos or muon antineutrinos, and compare the way in which they change their flavor. And the similar thing is being done in Japan in an experiment called hyperkamiokande, in which an accelerator near Tokyo is shooting to a detector that is yet 10 times again bigger than that super kamiokande experiment I showed you. So double beta decay is looking for a very rare radioactivity, something that would have a half-life of 10 to the 26th years or more. And that sounds impossible until you realize, if you remember that number, Avogadro's number, 6 times 10 to the 23rd atoms in a mole in other words, of grams of material. There's that many atoms in there. And so if you collect a lot of them, like tons of these rare materials, and wait for 10 years, you can have the possibility of measuring things, but you better get rid of all the other radioactivity, and that's why these are done in these underground laboratories. And these are examples of ones across the world: Japan, Italy, well, actually these two, it's not sure where they're going to be, and the SNOW experiment has been converted to study neutrinoless double beta decay in tellurium. Nuclear theory is very important in the process of understanding that. Okay, so let's go back here to this cosmic microwave background. It's very hot in the first place. You can see it's 10,000 C when it was at the 300,000 year point. It now has cooled off from the expansion to about 2.7 degrees above absolute zero, which is about minus 270 degrees Celsius, or some minus 400 degrees Fahrenheit. That has been detected in a remarkable way, and dark matter has an influence on it, which is one of the ways in which you can observe that dark matter is in existence in our universe. And dark matter is thought to play a big role in how the structure is formed of larger scale things like galaxies. So this is a picture of some remarkable data from a satellite, and satellites have been the answer to doing this measurement of cosmic microwave background very well. This satellite observed this 2.7 degree radiation across the whole sky. It's a Planck experiment, it's referred to. And this is the distribution of amounts of that particular light. And it only varies by parts in 100,000 or so. But if you plot the size of those dots that you see on that plot here, then you get quite a remarkable oscillatory pattern that looks like this. If you look very carefully, you can see there's little blue dots, which are the actual data, and the red spots are the averages of those points as a function of, in this case, a polynomial that's representative of the size of those spots. And what's remarkable is that this is fit by a model which has 6 parameters in it only, 2 of them being how much ordinary matter there is in the universe, and the other being how much dark matter there is in the universe. And then there's another quantity called dark energy that comes into this as well. And this fit is absolutely remarkable, but there are still many more experiments to be done, and Steve Choi here is working on those. So this dark matter material, why should I believe that it exists? Well, if you take a galaxy like ours, we can't actually look at our galaxy. We'd have to get outside of it in order to take a good picture of it. But it's basically, it's like a cinnamon roll. But when we look out on a night sky, you're looking along the axis of the cinnamon roll, and so it just looks like a patch of stars across the sky that we call the Milky Way. But it's a spiral galaxy, and if you plot the velocity of the stars, here is a plot for another galaxy like ours, you find that there just isn't enough mass in the glowing material to hold it into that pattern. You've got to postulate about 5 times as much material, represented by this curve, which they refer to as the halo, in order to fit the data. And similar things are inferred by using the imaging of galaxies behind other galaxies and comparing the distortion that happens due to Einstein's theory with the amount of light that comes, which is representative of the ordinary matter. You find, again, about 5 times as much dark mass as the glowing mass being what we're made of, ordinary matter. An example of the fact that it's very weakly penetrating is the fact that here's a picture of what's called the bullet cluster, where it appears as though 2 galaxies have passed through each other. The blue is the dark matter, which seems to have passed through very easily, whereas the red is the glowing gas, which is made of ordinary matter, which appears to have been much more impeded in the collision. And again, dark matter is weakly interacting, so we physicists love whimsy, and in this case we talk about dark matter being weakly interacting massive particles, in other words, WIMPs. So if you come right down to it, we're just a bunch of geeks looking for WIMPs. But the experiments to do it are extremely complicated, and they are the ones that are done in the underground laboratories. Our picture then of how the universe is composed has us only about 4% of the total, which is almost as shocking, maybe even more than Copernicus's idea that the sun is the center of our local solar system and not the Earth. 26% of the total universe being dark matter and 70% being something called dark energy, which it turns out is inferred from the fact that gravity isn't just attractive. I mean, you all learned in school that gravity is an attractive force between 2 masses. It varies as the square of the distance. It's product of the 2 masses divided by r squared, the distance between them squared. It turns out there's another repulsive force, which is referred to as, or can be described as, another source of energy in the universe that happens to be just the right amount of energy to have a closed universe, one that doesn't end up in, well, we think, theorists are still working on this, but the most common thought is that we don't end up with a big crunch at some point in the future. So we're looking for weakly interactive massive particles as one possible form of this dark matter, and the way in which we do it in our underground laboratories, we are moving through this galaxy, which has lots of dark matter. You just saw it in that first slide I showed you. And as we pass through it, we will bump into these weakly interacting massive particles, partly through to our own motion and partly through our motion through the galaxy. And what we try to detect is the very small recoils that occur when these dark matter particles hit atoms in our very clean, low radioactivity experiment. Now, in particular ones I work on, which are made of liquid argon, there's an additional trick for trying to get rid of radioactivity, and that is if you look at the light produced in the argon and digitize every pulse, the WIMPs produce very short bursts of light on the order of nanoseconds, whereas the light from other radioactivity is on the order of 1,000 times more. And so we can throw them away with, we throw away 10 to the 8th or 100 million of these pulses compared to one that we keep as dark matter. Very complex experiments. Some of the biggest are ones that use Italy, like the one I work on in Gran Sasso and have worked on in Snow Lab, and hope in the future to have an even bigger one in Snow Lab called Argo. That's called Dark Side. The LZ experiment in the United States in that same South Dakota mine, and the xenon N-ton with a significant US component in the Gran Sasso laboratory under a mountain in Italy are other examples. And you do it a little differently in xenon, but the idea is very similar. And there's a lot of both experiment and theory going on here at Riverside in terms of experimental cosmology. Now, dark matter, we don't know what it is. It could be a wide variety of things. WIMPs are only one example. There are other experiments happening looking for things called axions that are motivated by a different theory. The Large Hadron Collider has been looking for dark matter particles with the idea that maybe there hasn't been enough energy to produce dark matter particles since the Big Bang. And of course, it's the highest energy accelerator in existence right now. So let's look for some evidence for dark matter particles as collisions happen there. And so there are also a lot of people looking at evidence from dark matter from experiments done in satellites and so on. Now, gravitational waves, you'll hear a lot more about them from the real expert, Barry himself, later today. But they're a really remarkable phenomenon. I mean, the idea is that in the vicinity of a substantial mass, you can have a distortion of the space around it. And these black holes that are some of the most massive objects we know, when they collide with each other, they can produce a distortion of space that propagates as a wave. And when it gets to this very delicate instrument, one in Hanford, in northwestern United States, and one down in Louisiana, what's remarkable is that the signals that you see in those two detectors, one is blue and one in red, are essentially identical, very strongly defining something that is very different from any of the noise. And this has also now become a network of experiments, one in Italy, one being built in Japan, and in India. And so you'll hear much more about it from Barry. And it is one of the examples of what has come to be known as multi-messenger astronomy these days. A situation where all of the different ways of looking at our universe, at the space around us in different ways, in radio waves, which are just another form of light, as are the optical and gamma rays, and also now neutrinos. This is looking at this pancake of our galaxy and looking along the axis of it. We're using all of these particles, this one coming from IceCube. And again, a group of people that are working here at UC Riverside on this, covering a tremendous expanse from the smallest energy to the highest energy with 3 or 4 different techniques coming together. So, first of all, so this is my summary slide, which says there's been amazing progress. I mean, 60 years ago, the idea that there was a Big Bang really was in the early, let's consider it stages. These days, 60 years later or so, it's really the basis for our understanding of the universe, which is really it's really an existential question when you think about it. It's not just how were we created and come to be the way they are today, but how did everything get created? and come to be the way it is today? It's a very important question for we as humans to try to understand. Measurements of neutrinos, cosmic rays, dark matter, and gravitational waves will help us to understand that. And the proposed Experimental Cosmology Center here at Riverside will provide an excellent location for the development of equipment with students, hands-on here at Riverside, that will be part of these large-scale experiments that are at the forefront of the field. It'll train the next generation of students who go on to lead the experiments, and as well as theorists who will derive insights from the data and also work with students in a very cooperative way. So this establishment I can speak to from personal experience, in that we've had a similar institute at not just, it's headquartered at Queen's University, but it really goes across Canada, which the government has been funding. In fact, they just gave us another 5 years of funding, a total of $45 million, to support such work, because their recognition is that this is a rapidly expanding field. There's been 26 new faculty members in the field of astroparticle physics, as we call the general thing, in Canada in the last 7 or 8 years. Part of it supported or stimulated by the existence of the previous funding we had. Translate that to the US, that's as though you had 260 new people in physics departments working in this particular area. But the motivation in the first place, and the motivation that led to the extension, is the fact that the government recognizes that doing the sort of thing that you're doing here at the proposed Experimental Cosmology Center is essential if you want to get the maximum advantage out of the things that are being done in this field here in the US. LIGO, the underground laboratory at South Dakota, Fermilab, and a number of other things. And so you really need to be supporting the scientists at the universities and the laboratories at the universities, where things get developed on the small scale and translated to be part of a big experiment if you're going to be successful in this field. And so I'm very pleased to be here to honor Barry, but also to speak positively about what you're establishing here. It's a really good thing. I know that from personal experience. Thank you very much.
Thank you, Dr. McDonald. Now I'm delighted to introduce to you our next speaker, Professor Chang Jung. Professor Jung is a distinguished professor from State University of New York, Stony Brook. Professor Jung is a fellow of the American Physical Society, American Association Advancement of Science. Dr. Jung founded the Stony Brook Nucleon Decay and Neutrino Research Group in 1991 to study neutrino properties and search for proton decays. He and his group participated in various groundbreaking projects, including the Super Kamiokande, the K2K, and the T2K. We'll hear more about his work. What I wanted to also say is Professor Jung is also known as an amazing teacher. You may see him in various media outlets that interview him for his expertise in physics of sports, as well as elementary particle subatomic physics. He has recently received the American Physical Society 2022 Julius Edgar Lilienfeld Prize. I'll just read the quote. For outstanding contributions and leadership in experimental neutrino physics, and for outstanding teaching and outreach, especially in the physics of sports. Finally, I'd like to mention also Professor Jung is the chair of the Department of Physics and Astronomy at Stony Brook. Please welcome Professor Jung.
Which one is this is a pointer? Okay, and then the clicker. Which one is a clicker? No? Wait, okay. All right. It doesn't go back. All right, well, let's see. First of all, how's everybody doing? Doing good? Art talk was fantastic. And how many of you are from outside of university? Do we have any general public? Okay. All right. So it's my pleasure to be here, and also I'm deeply honored to be part of the celebration of Barry's National Medal of Science. And let me start with nothing. That's my favorite topic. Nothing. So what is nothing? This is my favorite Chinese character. In modern days, everybody should know a little bit about Chinese characters and stuff. And so this particular character symbolizes as nothing. This choreography is written by my brother who passed away last December for me. And this, when you combine nothing with this is heart, is nothing in your mind, or there are many different type of interpretations you can have. And this is kind of stage you have to go through to reach nirvana. Okay, so that's what this is. So going back to it, this nothing has been a subject of scholars in Asian culture thousands of years ago. They talked about nothing. And so we can imagine, is it a vacuum? So let's say in this room, if we seal it and then pump out everything and make it a vacuum, even we make it shielded for electromagnetic waves, so there's no electromagnetic waves. But if you wear God's a pair of glasses by God, and you will see vacuum is full of stuff. It has quantum fluctuations, dark matter, dark energy, which are talked about, and including neutrinos. So what I said, long story short, I thought about these things a long time. Nothing does not exist. But think about this separately. So here we have, in that nothing, a very small portion is in neutrinos. And when Barry got this national medal, this is what I think what they were having conversation. You know, Joe Biden say, man, you must love gravitational waves. I can't do his accent well, but then Barry says that, well, Mr. President, actually my favorite is neutrinos, okay? So this is actually true. So let's talk about neutrinos a little bit. Art has already talked about neutrino facts. I will say a few more things I would like to emphasize. Neutrinos in standard model has assumed it has no mass, and then it's very difficult to detect because it doesn't have electric charge, and it can actually, one neutrino can go through entire universe without getting lost. And because of that, when it is created deep inside stars or even whatever the heavy object, it can penetrate out and come to us. So this is the most reliable messenger in the universe, as well as we can study things deeply using neutrinos, which we cannot do it otherwise. One of the key things which I would like to introduce this word called so-called Majorana particle. Majorana particle is defined as a particle is the same as its own antiparticle, which are talked about. And this is a weird thing, so it could be in both. So it could be a particle or antiparticle in the same particle. And neutrino is a candidate to be a Majorana particle. This is a very important feature to understand the rest of our lecture and then what Art talked about. And as Art already talked about, as you should really try to do that if you stick your finger out like the fingertips, and at fingertips at every second there are 50 billion neutrinos passing by. You should be able to feel these things. I do feel that. Do you feel that? So, and then finally, there's a thing called the relic neutrinos. After Big Bang, there's about 1 second later, huge amount of neutrinos released. They are crawling around all space in the universe. And there are about 300 of them per square centimeters in this room right now. And then detecting this will be really, really tremendous discovery. However, this is such a difficult experiment. There are only a few people are thinking about it, doing R&D, but there's no really serious attempt has been made. I call this one as mother of all experiment. So some of you young people here, you can do that, you can get Nobel Prize, for sure. So let me start with historically how the neutrino came about. Around 1930, that Pauli, physicist Pauli, was looking at the experimental data of the tritium decay. At that time, the only known particles were proton and then electron and such photon. And so when tritium decays, at that point, people all assume it will just decay in a two-body, and then one of the particles coming out is electron, which is at the time called a beta particle. This beta particle should have well-defined energy. But then you do the experiment, what they find is a very continuous spectrum. So Pauli decided that it must be something's missing here. So it is really three-body decay, and one of the particles which is not seen is carrying that missing energy. And that he called a neutron. So most of you know, neutron, what we today call, is not that. And so Fermi came out later. Actually, Chadwick discovered a neutron before neutrino was discovered, and the Fermi named it as, because Fermi was Italian, he called it neutrinino, because anything ino is a smaller, right? So that's how neutrino name was came about. So here's the Pauli's letter he sent to a conference where he wanted to present his idea about neutron. So he wrote here, dear, look at the date, it's 1930. Dear radioactive ladies and gentlemen, he was a really geek. I mean, I will never write a letter saying that, radioactive gentlemen, all right? And then he says, I have hit upon a desperate remedy for this beta spectrum issue. And then he go on and describing things, actually quite many of them are remarkably accurate today. He even assumed the neutrino has mass, but although he predicted much, much higher than what we don't know today. And then he went and said, this is something important for theorists to hear saying. He said, but I don't feel confident enough to publish anything at this point. These days, people have some idea, they publish it next day without thinking, but he didn't publish. And then this one resonates with me. He said, unfortunately, I cannot come to Tübingen in person since I'm indispensable here at a ball taking place in Zurich in the night. And dancing was more important for him than going to conference. So I appreciate that. I feel the same way. So I would like to talk about neutrino is actually the most prolific particle generator in terms of generating Nobel Prizes. So these are some of the list of Nobel Prizes. First Nobel Prize was I have a hard time seeing this, 1979, given to Glacia Salam. Can I take this one off? They should be able to. Can you hear me? All right, so that's good, much better. So Glacia, Salam, and Weinberg received this Nobel Prize. And here's a quote. I'm not going to read the whole thing. The bottom line here, if you read the red, yellow one, is that prediction of weak neutral current. This is a part of the Standard Model they have established. This weak neutral current is, if you remember what Art has said, there's force carriers, and W and Z. W is a charge current force carrier. Z is a neutral current force carrier. And at that time, they predicted it. It was not discovered yet. In 1974, it was established. Barry has done an experiment with Scully at Fermilab, called E21. In that experiment, what they use, they have steel and a scintillator bar detector. And then they saw 400 GeV muon neutrino is produced and shot at the detector. And then for the charge current interaction, muon neutrino will convert into muons. So this is what charge current does. It converts muon neutrino into muon. So they saw that because this is a clear signature of muon coming out of this. So neutrino, you don't see coming in, there's no hits here. It hits and then muon comes out. So this was a charge current signature. But then they see occasionally, about 20% time, nothing comes in and then generates a blob and then nothing goes out. So this is a clear indication of the Z particle, neutral current was exchanged, and a muon neutrino comes in and muon neutrino goes out, and then by momentum and energy transfer, it creates stuff. That's what this is. So Barish's experiment actually contributed to discovery of neutral current. And then 1988, these people received the Nobel Prize for discovering muon neutrino. That was early 1960s. And then 1995, finally Fred Reiners received the Nobel Prize for detecting the neutrino for the first time, 1956. It's kind of, if you think about it, chronologically reversed, but there's a historical reason for that, but I'm not gonna go through all of this in this talk. So, and then on top of that, 2002, there was a Nobel Prize to Ray Davis and Goshiba for pioneering contribution to astrophysics and particularly detection of cosmic neutrinos. And then 2015, Gajita and then Art, who just spoke, received the Nobel Prize for the discovery of neutrino oscillations, which shows that neutrino have mass. So I will talk about this a little bit more. So the Fred Reiners and Cohen has done the experiment in 1956 or so. So this is the detector. They had a rather simple detector. It has blue target regions where neutron capturing medium is located, and then has detecting volumes and outside. And then inverse beta decay, neutrino will come in from anti-neutrino neutrino will come from reactor, and it interacts. It produces a positron and neutron. Neutron got captured, it generates a signal, and the positron will generate also two-photon signal by capturing annihilation. And by looking at these things, they were able to see existence of neutrino. So nice thing is this is a rarely seen historical thing that when they saw this neutrino, they sent a telegram. At that time, you could not text message with the iPhone. So using actually telegram, this is sent to Pauli. So it's hard to read it, so I will put it down here. We are happy to inform you that we have definitely detected the neutrinos from fission fragments by observing inverse beta decay of protons. Observed cross-section agrees well with the expected 6 times to 10 to the minus 44 square centimeters. This is incredibly small, the Reiners and Cohen. So that's the historic documents. And then there's a whole bunch of stories about their measurement quite didn't agree with the theory and the changing, but that resulted in actually, for him, Fred Reiners getting Nobel Prize up to 1995, very late. So here's another historic photo, which this is Maurice Goldhaber. This is Pauli, who invented the concept of neutrino. Pauli was visiting Brookhaven National Laboratory. Maurice Goldhaber is, in my mind, is one of the legendary giant in our field. And he was also director of the Brookhaven National Lab in its golden days. He also done an experiment. As soon as neutrino was discovered, he did an experiment to measure whether neutrino is left-handed or right-handed. The way left-handed, right-handed is defined is that momentum of direction of neutrino is going, where the spin lies. So spin is turning right sides, it's called right-handed. It's left opposite direction, we call it spin is opposite, we call it left-handed. And he did an experiment, and then he proved that neutrino is left-handed. So this is actually a photo of Maurice told me that he actually staged. So photographer passing by when they were talking. So Maurice Goldhaber said, Miss Radioactive, I think protons decay. He was also first experimental people thinking about proton decay experimental measurement. And Pauli said, you cannot be serious. You must be more desperate than I was when he invented the concept of neutrino. And then Maurice said, I proved that neutrino are left-handed as well. And then Pauli said, I think this is actually a true story. I heard that, truly amazing. I used to say, I don't believe God is left-hander. Okay. All right, so then let's move quickly to 1998. I call that neutrino revolution, observation of neutrino oscillations in the atmospheric neutrinos by Super Kamiokande. I was a member of that Super Kamiokande experiment. This is an experimental evidence for physics beyond the stellar model. So what happened is that 1970s, late 1970s, 1980s, that so-called granularification theorist has developed a theory which will unify many of our current understanding of weak interactions and then electromagnetism and then strong force of the QCD, and to make into one force, one theory. That is called the granularification theory. In that theory, when they developed it, they naturally found protons has to decay, almost all of those theories. So that prompted the experiments to go underground to build these gigantic detectors. Some are under water Cherenkov detectors, such as you see here, IMB, and then Kamiokande. This is built in early 1980s. And then some are still the detectors of Fred Hughes and Sudan. The water Cherenkov detectors were very successful. And then in the end, one of the magnificent detectors, Super Kamiokande, was built. I will talk about that a little bit more about this. And these detectors built for proton decay initially, we didn't discover proton decay, but it turns out actually neutrinos were nuisance because neutrinos will make a background to proton decay signature. But it turns out, even though we didn't discover proton decay, these detectors are so large, as you heard from Art, neutrinos doesn't interact at all. So you need a really huge element so that one of neutrinos, gazillions of neutrinos, one of them will interact and create a signal, and it will detect them. So it turned out to be these detectors are excellent detectors for neutrino experiment. So here's a Super Kamiokande. Super Kamiokande is 1 kilometer under the mountain in the west coast of Japan. It's huge. It's 40 meters diameter, it's 40 meters height, a cylindrical tank filled with 50 kilotons of water, has 11,000 20-inch PMTs, is photomultiplier tubes. That is the one detecting photons. And then it has an inner detector and an outer detector. This is what schematically looks like for the physics analysis. So I want to just briefly give you one little bit technical details of how we detect these things. Neutrinos doesn't interact anything. So imagine if you have this detector, gazillions of neutrinos are coming by, just passes by. It doesn't do anything. Occasionally, one of them will come in and hit, let's say, electron or any charged particle. Then it will kick that electron into the water. When that kick momentum is big enough, the electron, listen carefully what I say, electron in that water can go faster than speed of light in water. Faster than speed of light in water. If you heard a little bit about special relativity, nothing can go faster than speed of light. But in water, particle can go actually faster than speed of light because in water, speed of light is reduced by about 30%. So when you do that, it generates a very peculiar light called Cherenkov radiation. And those light is the one we are detecting. And then we analyze what happened in the tank. So you should, again, there are a mixture of Japanese, katakana, and then Chinese characters mixed together. And this thing is called a neutrino, all right? So then the light, Cherenkov light is generated, and then it goes into these photomultiplier tubes. This is 20 inches. And then photon will hit the surface of metal. It creates a so-called photoelectron. The electron is accelerated to the metal structure here, so-called diode. And then they hit next stages and multiply about to 10 to the 7. 1 becomes 10 to the 7, 10 million. And then we read those charge and time, and then we know what happened in the tank in terms of interactions. That's how we know whether muon neutron reactor, electron neutron reactor, or proton decay has happened. It's a very simple experiment, actually. So this is how you make a very sophisticated state-of-art detector in 30 years ago. This is a Japanese worker is blowing on the glass and to make a PMT. And now at that time, they could have built a factory. They said to make it precision, actually these workers can make it more precise than the factory can build, and factory cost a lot of money. So that's how they produced. So now let me talk about a little bit about atmospheric neutrinos. Atmospheric neutrinos are created, we have an atmosphere, and then protons and other elements are hitting this atmospheric, the molecules, or the atoms. Then what happens? So let's say proton comes in and hits, and then it will generate a whole bunch of particles called the pions. These pions decay to muon and then muon neutrino, and then muon will decay to electron and then electron neutrino and muon neutrino. So in this simple scheme of things, if you look at it, for every electron neutrino, there has to be 2 muon neutrinos. So that's a simple theory. Then you say, you assume that, and then you measure these things, and then you have the theory, you divide it by, if theory is correct, it should be 1. When you measure that ratio, we measured, say, historically, less than 1. And that caused the problem. Something happened that in this, the muon neutrino and the electron neutrino. So one of the explanations that came about is that here's a superconductor detector sitting on the ground 1 kilometer. Now, neutrino, because it doesn't interact much, it can come from the top, it can go through the Earth without being disturbed much. So neutrinos coming from the top. You can imagine it doesn't have the time. Imagine the neutrino oscillates into one type to another. Muon neutrino goes into electron or tau neutrino. If we assume the distance when they travel is not enough to oscillate, so let's assume neutrinos, muon neutrino came down from the top, is all detected as muon neutrinos. But you can imagine, in particular circumstances, muon neutrino come from the bottom, can turn into tau neutrinos. Some of them comes in from muon neutrino that stay as a muon neutrino, detected as a muon neutrino. Now, this detector is not capable of detecting tau neutrino, so that disappears. Then if you look at the muon neutrinos coming from the top compared to the bottom through the Earth, it will be 2-to-1 ratio. So if this is true, neutrino oscillation actually happens, then in this formula is actually which indicates how neutrinos oscillate between different species. You can see it here. I don't want to go through too much of the mathematics, but here delta m squared is a mass squared difference between 2 different species. So if mass is 0, all neutrino has 0 mass, this is going to be 0, neutrino oscillation will not happen. So if neutrino oscillation happens, the requisite is that one of the neutrino has to have a mass. This is why when neutrino oscillation was discovered, people say that is equivalent of discovering non-zero neutrino mass. Okay? So this was our conjecture, and then we did the experiment, look at the data. This is a little bit complicated, but the only thing I would like to pay attention to is here. If you look at here, muon neutrino that we observed, this side of a plot is the neutrinos coming from the top. This side of the plot is the neutrinos coming from the bottom. You can see the prediction is this hatched area. The cross is data. Coming from the top, prediction and then measurement is completely agree. But if you look at the coming from the bottom, it is a factor of 2 difference, exactly what we predicted. So that is indication of neutrino oscillation. You can do more scientifically, you can plot what kind of parameter space that is indicated. We did many different ways of looking at it, all come out consistently, and that made Super Kamiokande discovery, observation of neutrino oscillation, namely non-zero neutrino mass. So that has, 1980 paper had a tremendous amount of impact in not only in particle physics, nuclear physics, and astrophysics. And I should say, neutrino oscillation observed and established not only by Super K and Snow and other, is the only phenomenon beyond the model observed in a laboratory venue today. Dark matter, such a thing exists, but that's outside of our laboratory. On the laboratory, this is the only phenomenon. So here's Barry also comes in. Barry, the reason why he liked the neutrino is he also had an experiment called the macro that was actually looking for magnetic monopole, but that detector was also good enough to look at the neutrino oscillations, and that collaboration has analyzed neutrinos coming through the Earth mostly, and then they were able to set the allowed region, and with about 4 point some sigma, and this is a detector they use in the ground source laboratory. So they contributed to confirmation of atmospheric neutrino oscillation in the 2003 paper. So when this happened, I had a personal interaction of C.N. Young, which I will talk about a little bit more. C.N. Young is a remarkable theorist. Probably, I call him, after World War II, probably modern day Einstein. He has got Nobel Prize for parity non-conservation discovery theory. He has written Young-Mills theory that is a profound theory that impacts all modern theories. And then he also has something called Young-Baxter equation that impacts condensed matter physics and in many other areas. So he could have gotten 2 or even more Nobel Prizes. He was, I met him in 1997 on the parking lot at Stony Brook. So I said, Frank, I call him Frank, and the reason why he liked to call himself Frank is apparently he really loved Benjamin Franklin as when he was young. So that's why he took his name of Frank as an American name. And so I said, Frank, it looks like a neutrino has mass. And then Frank Young told me, it can't be. The mass of neutrino are so beautiful. He was a profound theorist. He also had this philosophically nature, there are certain order, certain beautifulness in the mathematical order. And then after 1980 and the Super K announcements, I met him again. I said, when I met him, he said to me, I guess you're right. Nature is mysterious in many ways. All right, and then finally, when I met him in 2016, he said, on neutrinos, even people like C.N. Young, profound thinker, that my intuition failed me. So this is what physicists, we should be humble. At the extent what we know, even the brightest, the deepest thinkers, we still don't know much about the nature and the universe. We should be always aware of that. So here's the actual C.N. Young sitting in his residence in the Tsinghua University in China. And this is when we met. We had like 4-hour nonstop discussions. He didn't even give me water or anything to eat. I was really thirsty, I remember. So, detection of astrophysical neutrinos and solar neutrino problem, I want to say a few words about this. So this started out with a brilliant theorist, John Bacall. He has set up something called the standard solar model. And then he literally single-handedly calculated everything's happening inside the sun in the fusion cycle, starting with a so-called PP chain. And this PP chain generates about 99% of energy. So his theory was well supported by heliosseismology measurements and other measurements. So we knew that his theory is quite good and correct. But then in this theory, neutrinos coming from the sun is a pure electron neutrino. There's no anti-neutrino or muon or tau. It's pure electron neutrino. So then people went out and measured these things. The first experiment, this is one of those experiments I will never dream about doing it. It's a crazy experiment. So the Ray Davis, he went into mine in South Dakota, where actually the June experiment has now modern detectors. He used 100,000 gallons of cleaning fluid, and then looking for solar neutrinos, sun coming from sun, and then interacting with the chlorine, and then producing argon, and then electron coming out. Now, this interaction is, he expected about 1.5 atoms a day. So when these things happens, he have to drain all these things and then chemically count these things actually happen. It's mind-boggling to me. You're gonna do these things. But he was originally, he was a chemist. And that's why he devised this thing. But he succeeded it. Here's the actually Ray Davis and John Bacall. They're together there. He did an experiment and he actually saw solar neutrinos, but the amount of observation he made was only about 1/3 of what John Bacall has predicted, as that was origin of the solar neutrino problem. So then many experiments is done. We put in a lot of effort, and then another thing which didn't convince that he saw solar neutrino was that because it's a chemical reaction here, it's not a real-time experiment. You cannot point where the neutrino is actually coming from. So then this is the Kamiokande experiment, which is the same as a super Kamiokande technology-wise. This experiment can see neutrino interaction in real time, and also you can see the direction. So neutrino coming from the sun comes into the tank and then hits electron, and the electron will take momentum because of momentum conservation. Generally, in the direction of sun, it moves. So if you know the angle of here, then you can actually point back whether it's come from sun. So when you did that, if you plot it here, this is the direction to the sun. You can see that majority of signal you're seeing is pointing towards the sun. So that convinced us the neutrino coming from the sun exists. And then the measurement of Kamiokande was also only about half of what standard solar model was predicting. So something's again wrong. And this is one of my favorite things. What this is, this image of sun seen underground with a neutrino. So if you think about my previous one, neutrino comes in and it hits electron, and electron will preserve its direction, right? So you can map it back, and you can construct a sun image. So this is what it looks like in a neutrino's point of view. And then poor thing is that the 1 pixel here is the size of sun. So the resolution is very, very poor, but it's beautiful, okay? So many experiments has done. So these bars are representing the theoretical prediction, and then the blue ones are the experiment has done various experiments. And you can see experiment and the theory does not agree. So it has been going on for 20, 30 years. But then Art McDonald and Snow came to the rescue. So this is the solution to solar neutrino puzzle was made by Snow. Finally, when they came in Snow was ingenious experiment. Actually, one of the researcher in the UC Irvine proposed that experiment originally. And then in that experiment, you can measure all neutrino types. Electron neutrino comes from the sun. If it oscillates into muon or tau, then they can actually see all of these things. They can count all of them even though they changed. By doing that, they were able to say, bang, nail to exactly what theory is predicted. They measured all of that experimentally. So it just cleared up the whole solar neutrino problem, and then that resulted in a Nobel Prize, right? So before that, another remarkable thing happens with this large version of detector, the neutrino detectors underground, is that 1987, February of 1987, something remarkable happened. Typical sun can live 2 billion years. You think about these numbers, right? 2 billion years it lives. And then it burns from PP chain, proton and proton, and then go up the heavier element, go to silicon and iron. But at that point, they cannot burn anymore because of binding energy differences. So it stopped burning, it lost all the energy. The only thing left is gravitational force. So whole star, huge star collapses, and then when it collapses, so much of energy, kinetic energy, potential energy is accumulated at the center, it bounces back and shock wave generated, it blows star apart. That is the supernova. So supernova was predicted and theoretical models there, And when supernova happens, 99% of energy of supernova is released by neutrinos. So these were all predicted. And then February 1987, this supernova happened in a large magnetic cloud. You can see this is before supernova, this is after supernova. I think one supernova, if I remember correctly, brightness is equivalent of the entire galaxy. There's a huge amount of energy released. More remarkable thing is that after 2 billion years, when this happened, the energy released by form of neutrino in 20 seconds, 10 to 20 seconds, that's it. Very short period of time. So this is a remarkable prediction by theory, but then we have seen that neutrino with the experiment, these experiment by Kamiokande experiment, water Cherenkov detector, IMB is also original water Cherenkov detector in the United States, and then Vaksan, the detector in Russia. So they see these are the data what they had. This is time, 0, 2 seconds, 4 seconds, and 12 seconds. All of these things came in within a little bit over 10 seconds. It's a remarkable thing. Think about it, 2 billion years of life, and it resulted in the explosion of about 10 seconds. So this one was measured, and then this was the first astrophysical neutrinos other than sun was made by any detectors, okay? And then this one was a remarkable confirmation of the core collapse supernova theory. So with this, Ray Davis and Goshiva, who was a leader of the Kamiokande experiment, received the Nobel Prize. And then their citation, which I already read before, for discovering astrophysical cosmic neutrinos. And at the time, however, remember, Super Kamiokande discovery of the neutrino oscillation happened in 1998. SNO was 2001, 2002. And so people thought this award was given, prize was given for neutrino oscillation discovery. But it wasn't, this wasn't that. Actually, in 2015, Gajita, who was a leader of Super Kamiokande, Art and Snow, received additional Nobel Prize for specifically discovering neutrino oscillation. So then, when that happened, the global race for further exploration of neutrino oscillation and what it can do for other scientific phenomenon. And so this is what happened. So here's the Super Kamiokande, and there's snow around that time. And these are all the experiments built in the world. I cannot obviously go through any of these things, but you can see. And these are these are partial list. It skips many of them, especially I don't include any double beta decay experiment, other experiment what Art talked about. And then many of these experiments establish neutrino oscillation further and further, more and more detail. We know a great deal about the neutrino oscillation now. And then ultimately, now we are at the stage to see Dune and Hyper-Kamiokande and Juno, which will be online next within 5 years. It will further explore neutrino oscillation. So here's because there are so many experiments, so many ways of doing things, I would like to give you some, in terms of simple picture, you can just get the idea of how complex it is, how many ways of looking at this. Neutrino has 3 types, electron neutrino, muon neutrino, tau, and then neutrino and antineutrino, right? It turns out they can oscillate many ways. You can, muon neutrino get to tau neutrino, muon neutrino can the electron neutrino, anti-muon neutrino can also oscillate, electron neutrino can go to nu muon nu tau, anti-electron neutrino can go to, these are all coming from different sources, sun, reactor, atmosphere, accelerator, all of that. So there are many ways of exploring the neutrino oscillation and learn about that properties. So one of the key experiments I was involved in is the T2K experiment. This is an experiment to generate neutrino beam using 30 GeV accelerator in the east coast of Japan called JPOC. And then you hit the target and generate neutrinos. You detect it first in the JPOC site with a near detector, and then you know what is going out. and you send it through the Earth, 295 kilometers to west coast to the super Kamiokande detector that I already talked about. And then you measure and then see if anything has changed. So main goal of this experiment was looking muon neutrino generated here, turning into electron neutrino and then come out here. So that was one of the main thing we were looking for. So indeed, we observed that. After turning on the beam, within 1 year or so, we saw 6 electron neutrinos appearing from muon neutrino, and a few years later 11, and finally 28. And then this established, for the first time, actually neutrino is changing flavor from one to another in a controlled experiment. This is observation of electron neutrino appearance from a muon neutrino beam. So with that, also many other experiments has contributed neutrino oscillation understanding. So K2K, T2K, SNOW, Kamlan, Diabe, all of this experiment have received so-called modern-day Nobel Prize, Breakthrough Prize in fundamental physics. And the citation I like is that for the fundamental discovery and exploration of neutrino oscillations, revealing a new frontier beyond and possibly far beyond the standard model particle physics. So now, what do you do? We basically explored everything. Now, one of the things which Art had mentioned, I would like to say a little bit in a different way. When Big Bang happened, its energy is so high and temperature so high, there's no reason why we believe there's a discrimination, bias, between matter and antimatter, particle, antiparticle. So when Big Bang happened, there must be equal number of particles and antiparticles created, antimatter. Somehow they have to evolve. But now characteristic of particle and antiparticles, when they see each other, they annihilate, they become light. So if that's the case, we shouldn't exist here. But somehow 13.8 billion years later, we don't see any antimatter. Everything was BC, including UC Riverside. Last time I checked, these are all matter. So you are matter and everything is matter here. So what happened to this antimatter and how we get here? So this is a profound question, probably one of the most profound questions in science. So this is what we think, okay? There's a reason why I told you about neutrino can be so-called a Majorana particle. That's what the Art is doing. One of the neutrinos, the beta decay is trying to establish neutrino is really Majorana particle, meaning neutrino can be its own antiparticle. This is a very important part. Now, let's assume neutrino is a Majorana particle, and it has cousin, which has a huge amount of mass, close to grand unification theory, 10 to the 14 to 16 GeV. So imagine, we can imagine after Big Bang, this huge energy, the mass, neutral lepton, which is cousin to a neutrino, is generated. They are Majorana particles. So there are particle and antiparticle, they can decay into neutrino or anti-neutrino at the same time. So but in our theory, we can imagine this is decaying to neutrino and Higgs, and anti-neutrino and Higgs, slightly different rate. This is allowed so-called CP violation scheme. The CP violation is basically saying charged particle and antiparticle behave slightly differently. So this allows neutrino is slightly more neutrino has survived than anti-neutrinos. It creates imbalance in the universe. So pictorially, you can imagine this. You can imagine in the very beginning of the Big Bang, there was matter and antimatter. And then there's a billion, and there's antimatter. Matter is like tiny little bit, 1 part billion more than antimatter. And then they will see each other, they will collide, and they all turn into light. But because the matter will have a little bit of excess that remains, that's us. This theory is called leptogenesis. There are more complex than this theory, but I don't have time to go through all of that. So because this to happen, key thing is the CP violation. And then we need to establish that actually neutrino in the lepton sector, CP violation does occur. And this is why we are gearing a lot of our resources and energy for next generation experiment to discover CP violation in neutrino sector. So how do we do this? So this is the same diagram I show you. Now we particularly look for accelerator-generated muon neutrinos that will mostly oscillate into tau neutrinos and anti-muon neutrino with anti-tau neutrinos, but sometimes small amount will oscillate into electron neutrinos. This is what we discovered in a T2K experiment. Now, we do it on purpose, muon neutrino, and look at appearance of electron neutrino, compare that with anti-muon neutrino appearing as anti-electron neutrino. If CP, charge parity, is conserved, they should be same, but if they are different, that the CP is violated. Again, they are more complex than this, but this is a fundamental idea. So we want to do these things, but to do this, you really need big detectors and powerful accelerators. And first, there are two large experiments. To be fair, I will talk about both. One is in a hyper-Kamiokande experiment in Japan. This uses the same accelerator used for T2K, but they are building a new detector, which is 20 times larger in terms of visual volume, 200 kiloton of water chunk of detector, and the nearby super Kamiokande detector. So that, with a basically larger version of T2K, they were trying to measure CP violation, and also they would like to see neutrinos coming from supernova, and also proton decay. What is important for this UC Riverside and the US community neutrino physicists is the Jung experiment. Jung experiment is a flagship experiment, particle physics experiment in the United States, based in the United States. We are putting in huge amount of resources, both financially and in terms of the person power and in terms of priority. So in this one, we generate a neutrino beam at the Fermi National Lab, that is in Chicago. And then it is a bend up to the hill, sand hill, that's why we call it dune. And it hits the target, and then we'll detect it with a near detector. Again, before it oscillates, we characterize its properties, and then send 800 miles underground to the South Dakota Sanford lab. And then we have a huge detector there. The detector we are using here is not a water chunk detector. It's called a highly advanced technology, state-of-art technology, liquid argon TPC, time projection chamber. We will have it gives like photographic image of the neutrino interactions. It has 4 caverns and a central utility. These are the thing. The length of this is about 60 meters each, so total is about 140 meters. So it's a gigantic liquid argon cryogenic detector. If we send a neutrino beam, we can measure CP violation, that's what I was talking about, but also we can measure mass ordering, meaning which neutrino is heavier, that we don't have clear idea. And then we can also look for supernova, neutrinos coming from supernova core collapse. So these are the kind of things what we like to achieve with this June experiment. So this is like hot off the press. You are a few people actually seeing it for the first time. This is the status of excavation of June far detector. This is about 140 meters, and this is about 15 meters, and then another 15 meters square, and like that. So this is a northern cavern. This is a south cavern. This is a central utility cavern. So it's getting there. We are probably start taking data about 2028 or 2029. So before I have a few more slides, more personal comments, but let me summarize some of this. Since the 1990 neutrino revolution, we made a remarkable progress in understanding neutrino properties and its implication on our understanding of the universe. We are at an unprecedented time in neutrino physics. The next generation experiment, Juno, which I didn't have time to talk about in China, Hypercare, June are coming soon. The combined cost of these experiments are staggeringly $5 billion. Okay, we're spending quite a lot of money. And both expected and unexpected discoveries are highly anticipated. And in my view, exciting times ahead of us. So-called, in my claim, second golden period in neutrino physics is coming, 2028 to about 2043. First golden period was 1998 to 2013. At this point, I would like to introduce Professor Annika Speer, who is a UCR Distinguished Teaching Professor in the Department of Theater, Film, and Design, Digital Production. Read my favorite poem. This is actually the only poem I know written by a legitimate poet about elementary particle, especially neutrino.
Thank you. Thank you. Cosmic Gall by John Updike. Neutrinos, they are very small. They have no charge and have no mass, and do not interact at all. The Earth is just a silly ball to them through which they simply pass, like dust maids down a drafty hall, or photons through a sheet of glass. They snub the most exquisite gas, ignore the most substantial wall, cold shoulder steel and sounding brass, insult the stallion in his stall, and scorning barriers of class infiltrate you and me. Like tall and painless guillotines, they fall down through our heads into the grass. At night, they enter at Nepal and pierce the lover and his lass from underneath the bed. You call it wonderful. I call it crass. Thank you.
Fantastic performance. I could not do that. That's why I asked her to do it. So the remarkable thing is this was written in 1960, not that many years after neutrino was discovered. And then, of course, at the time, he thought neutrino has no mass, which now we know it's wrong. But at the time, it was assumed to be no mass, including C and Yang. And then if you read it, it's really written well, because he really understood most of the really property of neutrinos quite well. And so this is not just somebody just jotting down. This was actually a serious poem written by a poet. So, all right. So in my life, I had many different physicists. I the opportunity to work with a great physicist. I sort of count about 3 people who I consider true giants in physics, and I have privilege to get to know them well. First one is a C.N. Yang, and which I talked about. He, in my mind, is probably one of the most profound thinkers in history of particle physics. Maurice Goldhaber is one of the legend. He's one of the cleverest experimentalists who devised a devilishly ingenious experiment. This is actually quoted by Frank Yang. And I had the privilege of knowing him and being a friend for a long time. And finally, Barry Barish. In my mind, he's one of the most exceptional and effective leaders in our community. Not only he has a knack of smelling good physics, you go for that, but also at the same time, he knows how to execute. This is my opinion, having a great idea is hard, but executing it can be even harder, especially in modern science. So this is not often valued or cherished and honored, commended, but I believe this is a really important part of modern science. And so this is 3 people have influenced me in many different ways, and it's my pleasure to get to know them. So here's However, it's interesting is that Barry Barish and I, we are sort of accidental friends. What I mean by that is that we never worked together. We never collaborated together. We never went to college, like Art went to Caltech together, but I never, so I don't know. We have no reason to be friends. But, but what we did, we just met each other in committees and panels and things. And then when COVID hit, I think, I don't know, I suggested or he suggested, we were talking, I said, well, why don't we have some sort of regular Zoom calls, no agenda, every 4 weeks. And we religiously did that. Every 4 weeks, we'll call each other and talk something. And then, so one of the things is that, I mean, he has been a great mentor to many different people, advised them. But when I decided to take on chair's position at Stony Brook, I went against his advice. He told me that, don't be that. I mean, chairs work for me, and why do you want to work for anyone else? So, but then I went against his advice, I became a chair, then I asked him to be my special advisor. So that's our relationship. And he calls me boss, but he also says that he's my boss. So we have that sort of mutual relationship. We share a love for neutrinos, solving the profound mystery of a matter-dominant universe, which I talked about. Passion for teaching. I love the teaching, and Barry as well. And he will not miss any of the classes for functions and things. And so I really appreciate that. Not only at Stony Brook, he teaches a graduate course, he voluntarily agreed to teach undergraduate course. So it's amazing. All the assistant professors and people want to get out of teaching. Nobel Prize winner is the only one who wants to teach more. So, and the dedication to public higher education, I will show you this video. Hopefully it will play. And an interest in sports and arts, and etc. Does it play?
And I think that represents kind of community that is attracted to Stony Brook. Luckily, we have a similar system in California. I went to public schools. When I was young, I thought I was going to be a tennis pro. Then I thought I was going to write the great novel when I got a little older. When I failed at both of those, I went into physics. I used the University of California system, which is very much similar to what's being done here, using in the state taking responsibility for upper education for the public and not just private elite schools. I mean, the East Coast is full of private elite schools, but Stony Brook is a real move in a direction that I know very well in California, where we do a pretty good job of enabling students of all economic and backgrounds to get a higher education. So my own life was transformed by being in Berkeley. I started not to be a physicist. I became a physicist by exposure in Berkeley. I found her in Berkeley, so Berkeley transformed my life, which is similar to Stony Brook. So a public university supported by the state that I couldn't have gone to otherwise with the family I came from. I somehow found physics along the way and have pursued it ever since.
So, actually, I would like to give him a round of applause. In my mind, we need more public affordable education, higher education. That's really critical for in terms of if you want to achieve diversity in many different things. This is really core in our system, how we can do that. So this photo was already shown before. It is one of my favorite photos. I'm not sure about his form. It's good for tennis form, but I'm glad he didn't decide to become a tennis pro. Okay, so that's good. So let me finish up saying that I send exceptional congratulations to Barry on your National Medal of Science. I'm very, very happy that I got to know you, be a friend. Thank you.
Thank you, Dr. Jung. And now we'll have a very short break for refreshments. So let's take about 10 minutes. And before that, after that, we'll have Professor Barish and a few of our faculty presenting after the break. So there are some light refreshments right at the lobby, and let's come back in 10 minutes.